Okay. So everyone can see the screen, right? Presentation ellarkum കാണാമല്ലോ. There is no issue with that. Everyone can see, right?
Yes, sir.
Okay. So now I will be just presenting you the screen. So what you have to do is I won't be able to see your chats now. ഓക്കെ, നിങ്ങൾ ഇനി ചാറ്റിൽ ഇടുന്നത് എനിക്ക് കാണാൻ പറ്റില്ല. സോ നിങ്ങൾക്ക് എന്തെങ്കിലും ഡൗട്ട് ഉണ്ടെങ്കിൽ നിങ്ങൾ അൺമ്യൂട്ട് ചെയ്തിട്ട് എന്നോട് അത് ചോദിക്കുക. ഓക്കെ, സോ ഐ വിൽ നൗ കണ്ടിന്യൂ വിത്ത് മൈ ഡിസ്കഷൻ ഓൺ ദിസ് ടോപ്പിക്. So let us look into the anomalous properties of lithium metal. Okay, let's look at these. And when I tell the term anomalous properties, what do you mean by that? Some properties that are exclusively that lithium metal shows, or we can say certain peculiar properties that lithium metal shows in comparison to rest of the elements in the group 1 uh, group. Okay, so that particular thing is what we are going to look into. Okay, so one of the peculiar property is that regarding to its melting and boiling point. So if you remember when we discussed the melting and boiling points, if you remember the digits that I wrote, these melting point and boiling point for lithium metal was very, very high in comparison to the other uh, other elements in that particular group. So lithium metal exhibit a very high melting and boiling point. So this is one of the important characteristic in comparison to other elements in the group, like the sodium, potassium, rubidium, cesium. In comparison to that, lithium exhibit very high the melting point and boiling point, probably because of very high cohesive energy, that is on account of its very, very small size. Okay, so that is one important peculiar property that the lithium metal shows. Another peculiar property is its hardness. Again, this hardness is because of the high cohesive energy. The lithium metals are very hard in comparison to other elements. You probably know that because sodium are very soft. You can easily cut sodium metal. Likewise, the other elements like potassium also are very soft metals. But in comparison to that, lithium is comparatively opposite. It is very, very hard. You cannot cut using a knife lithium metal. It's that much hard. So that property, again, the high melting point, is all because of its small size. It is exhibiting very high cohesive energy. So probably that is the reason why it is showing very high trends in both these properties in comparison to rest of the elements in the group 1. Moving to its reactivity with oxygen. So when we discussed the reaction with oxygen, I told you the reactivity pattern of different elements, how it reacts with air, and what all the products that you can expect. So when lithium metal reacts with oxygen, it usually forms monoxides. It has a tendency to form more of a monoxide. And the reactivity is kind of a little bit gentle. It is not very harsh reactive. However, when it comes to peroxide, the peroxide formation when lithium reacts with the metal ion is very, very less. Like peroxide formation is difficult. Though it is formed with little bit difficulty. However, superoxides of the lithium metals are usually very, very unstable. Okay, so regarding the stability, if we talk about monoxide, peroxide, and superoxides of lithium metal, monoxides of lithium metals are very, very stable. Now, you would ask me the reason for it. So I would say that when there is a equal size distribution of the cation as well as the anion, the lattice energy would be pretty high. And if there is too much disparity in size between the lattice in the cation as well as the anion, the lattice energy would be a little bit lower inside. So if you compare the sizes of O2 minus, that is mono in case of monoxide, or in case of superoxide, which is in case of peroxide, that is O2 minus, and in case of superoxide, which is O2 minus, the sizes is pretty increasing in this particular order. And if we keep lithium ion constant, lithium would be almost like having a comparable size with O2 minus, which would be smaller in size compared to these larger molecular ions. These O2 minus and O2 minus, they have larger anionic structure. Okay, so they form a lesser lattice energy when it forms a compound with the lithium ion in comparison to it forming the compound with a smaller oxide ion. So probably that is one reason why monoxides are more formed in the case of lithium in comparison to the peroxides or superoxides, where the size of the anions are pretty bigger in comparison to the lithium. So the lattice energy that is holding them would be comparatively lesser in comparison to the monoxides. Okay, so that is one reason why you have the monoxide forming more in comparison to the peroxides and the superoxide. Okay, so lithium oxide's reactivity is like that, and it is very peculiar because as you go down the group, like in the case of sodium, more of peroxide is formed, and the other higher elements, it is more of superoxide that is formed, okay, in comparison to the monoxide. Though monoxide is possible in the other, but more of peroxide and superoxide is what you will find in the rest of the elements in the group 1. So lithium only forms more of monoxide, but lesser of the super peroxides, or comparatively no superoxide in the case of lithium, because they are very, very unstable. Now, if we compare the basicity, when we discuss, I also discussed with you the basicity of the, when we discussed the reaction of the group 1 with the water, that time I talked about the hydroxide. So lithium hydroxides are very, very less basic. And because of that, their salts, that whatever lithium salts that are formed are pretty unstable. So that is why whenever you have carbonates of lithium or nitrates of lithium or hydroxide of lithium, if you gently heat it, a very gentle heating if you give, you don't give any strong heating, but simply a gentle heating if you give, it is converted to lithium oxide. Okay, so this is a very natural reaction that it undergoes. That is because of the stability of, probably because of the stability of the lithium oxide, and the less basicity is what the reason given. If the salts are less basic, then their salts would have a tendency to go into their oxide state. So that is one reason that is given. And apart from that, if you compare the carbonates and nitrates, these are larger anions, okay, and lithiums are smaller anions, okay, and therefore also they have a tendency to decompose quickly in comparison to the lithium oxide. So they will all decompose to their corresponding lithium oxide. Okay, so carbonate, when they decompose, there would be one more carbon dioxide also coming out. However, in case of nitrates, apart from lithium oxide, you will have the liberation of nitrogen dioxide as well. Okay, so there would be other substituents also, but in general, the salts would be decomposed into their corresponding oxide. That is, lithium salt would be decomposed to their corresponding monoxide on gentle heating, apart from the other side products that are formed in this particular case. Another effect of less basicity, and as a result, the instability of the salts, is that when we find lithium hydrogen carbonate, that is bicarbonate, we know, you know that sodium hydrogen carbonate, sodium bicarbonate, or potassium bicarbonate, they all exist in solid. Okay, however, lithium bicarbonate cannot exist as a solid. You can only get its solution by some method, but you cannot crystallize lithium hydrogen carbonate because of the instability of the lattice lithium bicarbonate. Okay, so these are some of the peculiar properties that the lithium only shows in that particular group one. Others are completely opposite to what you see here. Unlike sodium carbonate or sodium nitrate or sodium hydroxide, they all exist in solid state, and they all can be oxidized to their corresponding oxide, but not with gentle heating. But strong heating only, they would be converted to their particular oxides. But only in lithium case only, just a slight heat itself decompose the salt into their corresponding oxides. So this difference you should remember. You can convert the other metal salts also into their corresponding oxides, but only under strong heating conditions. Okay. But lithium being so unstable, other the salts of lithium being so unstable, therefore they can be easily converted to their monoxides. Okay. So I hope you understood the discussion so far. Then another property that the lithium metal shows, this I have already told you before when we discussed the lithium reacting with air. So in air you have nitrogen component, right? So lithium only shows this property of formation of lithium nitride, which is ionic in nature. So these lithium nitrides are formed only by the lithium metal in the group 1. Okay, other elements in the group 1 doesn't form nitride with reacting with the nitrogen. So this particular property is exclusive for the lithium. However, group 2 elements also shows this property where it reacts with the nitrogen to form their corresponding nitrides. However, only in group 1, only lithium shows this particular property. Another property that is shown by lithium only is that lithium reacts with carbon. When you heat lithium with carbon, you have to heat this. Okay, so when you heat lithium with carbon, what do you get? You get lithium carbide. This is called lithium carbide. Lithium. Please bear with the spelling mistake. Carbide. CARBIDE. Okay, lithium carbide. Okay, so lithium when you burn it with carbon, it forms lithium carbide, and this particular property is also shown by group 2 elements. However, if you heat sodium, potassium, rubidium, or cesium with the carbon, it doesn't form the carbide. However, you can form carbide with sodium only if you react your acetylene, that is your C2H2, which is nothing but acetylene varna. It's an alkyne, right? You have the H. This is your acetylene, right? So when you react with this with sodium, okay, in liquid ammonia, only then you will have the formation of your one particular compound is sodium hydridocarbide, and further if sodium reacts, it forms sodium carbide. Okay, this particular reaction is possible because of the acidic nature of these protons. Okay, because of the acidic nature of this proton, these can easily remove this H plus, and you have the sodium getting substituted in the places the cation. Okay, so this is called sodium hydridocarbide, and this is sodium carbide. So you can form sodium carbide, however, not by burning with carbon, but just by reacting with the acetylene in liquid ammonia. Only then you can form these particular carbide ion. Otherwise, The usual reaction that the lithium metal that it burns with carbon to form the carbide is not possible in the case of the other elements in the group 1. However, group 2 elements can react with carbon to form their corresponding carbides. Okay, so this is a very important peculiar property that only is shown by the lithium elements. So please remember these reaction, like you can form carbide, but it is via another route, that is reaction with acetylene. Acetylene reacting with sodium in liquid ammonia to form the first, initially you will form the sodium hydridocarbide, and then further reaction will give you sodium carbide. And in this case also you can form sometimes lithium hydridocarbide. Lithium hydridocarbide also you can form in between. So lithium hydridocarbide also you can form, and this lithium hydridocarbide is actually used in the synthesis industrial preparation of vitamin A. Vitamin A യുടെ industrial synthesis നിങ്ങൾ lithium hydridocarbide use ചെയ്യും. Okay, so just remember this fact. I have seen in one of the competitive exams they have used this kind of thing. Okay, so lithium hydridocarbon is used in the industrial synthesis of vitamin A. Okay. Now, another important property that lithium shows is its ability to form coordination complexes. Its ability to form coordination complexes. So in this, you can see one of the coordination compound that lithium forms is lithium ammoniated coordination complex it forms. Now, why they show so much good tendency to form coordination complexes is because of its smaller size and higher charge density. And because of this higher charge density, it shows this property of coordination complexes. Because of higher charge density, it can increase its attraction towards the ligands like ammonia or water molecule, any different types of ligands which are electron rich. Those can be pretty closely attracted to, so they can easily form a complexes. Now, one thing that I would like to bring in here is the lithium or any of the elements in the second period, any of the elements in the second period, they will all form coordination complexes in which the coordination number would be nothing but 4. Now, if you ask me why only 4 is formed in the case of group second period ഉള്ള എല്ലാ elementsum coordination complex form ചെയ്യുമ്പോൾ അതിന്റെ coordination number is usually 4. Now, if you ask me why that is so, that is because it is the second period. So second period has only 2s and 2p orbitals. So how many electrons it can accommodate? This can accommodate 2 electrons, this can accommodate 6 electrons. So there can be accommodating only 4 pairs of electrons, 1 pair in 2s and 3 pairs in the 2p. So only 4 pair of electrons can be accommodated in the second period. So that is why lithium metal, since in the second period, it can accommodate only 4 pair of electrons. So 4 lone pairs only it can accept from the ammonium. And that's why only 4 ammonia molecule it can accommodate. And that's why coordination complexes usually formed with the elements in the second period have a coordination number of 4. However, you will find that some of the lithium compounds like alkylated lithium, that is, this is a lithiated metal in which if you look, coordination number of lithium would be higher than 4. ഇതിൻ്റെ അകത്ത് ഇപ്പം നോക്കുമ്പോൾ 1, 2, 3, 4, 5, 6 coordination. ഒരു particular lithium atom എത്ര other atom node surrounded ആണ് നമ്മൾ നോക്കുമ്പോൾ approximately 6 is here you will find. But it is not because of it is expanding its valency or something like that, because it cannot expand its valency, because it is a kind of only accommodate 4 pairs of electrons. Now here this extended coordination is possible because of it is not a usual 2 electron bond. It is not a 2 electron 2 center bond, but rather it is a multi center two electron bond, something like that. That's why it is able to show higher coordination number. It is not the usual two electron, two center bond alla, but it is a multi center two electron bond. And that is why you see a higher coordination number. So you shouldn't confuse that the why lithium can form higher coordination number than 4. It is not possible. It can usually in coordination complexes, it will only form a coordination number of 4 because it cannot accommodate more than 4 pairs of electrons. That is the reason. So alkylated methyl having higher coordination number is only because it's a not the usual two electron two center bond, but rather it's a multi-center higher electron bonds. Okay, that is why you see higher coordination number in such compounds. So don't confuse that with the coordination complexes. Now, if you look at the other salts like carbonates, lithium phosphates, or lithium fluoride, they are completely insoluble. However, if you compare the same salts of sodium, potassium, rubidium, and cesium, they are all soluble in water. However, the carbonates, phosphates of lithium, they are completely insoluble. Even lithium hydroxide is only sparingly soluble. However, that is again the reason why lithium hydroxide is very less basic, because they are very less soluble, sparingly soluble. And this type of property you will also find in the element that is magnesium salts, which is an element of the second group. So second group magnesium salt in the salts insoluble on water. So they show a kind of similarity in properties. Further, if you come here, the halides or the alkyl lithium compounds, they are exhibiting the properties of exhibiting a covalent property. Now, why lithium compounds, lithium halides ആയാലും lithium alkyls ആയിരിക്കും അത് എന്തുകൊണ്ടാണ് അയോണിക്കിന് പകരം കോവാലന്റ് ഷോ ചെയ്യുന്നതെന്ന് നിങ്ങൾ എന്നോട് ചോദിച്ചാൽ അതിന്റെ റീസൺ നിങ്ങൾക്ക് പ്രോബബ്ലി അറിയാം. ദിസ് ക്യാൻ ബി the reason is because of the smaller charge and higher charge density. So you know Fajan's rule. If you remember the Fajan's rule, one of the rules states that if the size of the positive ions becomes smaller, so what happens? The polarizing ability of that anion becomes high. So when polarizing power of the cation increases, what happens? It has a tendency to form more covalent bonds. So that is why when lithium forms the compounds with larger anions, this is important, okay, because larger anions have higher polarizability. So when lithium forms compounds with larger anions, be it halides or be it alkyls or be it chlorates, okay, larger anions are very large ions. So basically halides is what generally told, halides and alkyls. Lithiumത്തിന്റെ കൂടെ compound form ചെയ്യുമ്പോൾ they always have a tendency of covalency. And that's why, since they are covalent in nature, that's why they would be highly soluble in organic solvents like acetone. Okay, so this property is also you will find in magnesium. So this lithium perchlorate as well as magnesium perchlorate, they have similarity in property that they are soluble in acetone and they are kind of covalent in nature. Okay, so these are some of the very, very peculiar properties that these lithium metal shows. Okay, now what I would like you to do now is another property, which is lithium ion are heavily hydrated. This we have already discussed previously, that lithium ions usually shows very high hydrating power. So this we have discussed because of high charge density, it is solvated much with the water molecule. Okay, so now what I would like you to do is find me, why do you think all these peculiar property that you see here is shown exclusively by the lithium metal but not by any other elements in the group? Now I would like you to reason out why that is so. That reason I would like you to tell me now. So I have discussed with you all the peculiar properties that these particular elements show. Now, kindly tell me what is the reason behind lithium showing such peculiar property? Can anyone tell me why does the lithium show such peculiar property? Another thing that you found while I discussed the peculiar properties is that they have a relationship with the magnesium, okay, which is kind of diagonally present. Okay, if you see the positioning of lithium and the positioning of magnesium, they are diagonally related in the periodic table. Okay, so magnesium and lithium also show some great similarity with each other. Okay, so now why all these things are coming into the picture? So since you have already learned about these, I would like you to answer me why these things are observed. Okay. So some of you are saying that it is because of small size and high ionization energy. That is perfectly fine. Lithium have exclusively smaller size and higher ionization energy. That is what is responsible for the peculiar properties that lithium shows, especially when we talk about the high melting point and boiling point and about the hardness. That is all exhibited because of, as well as the high hydration energy, all those property and covalency is all the reason because of small size and very high ionization energy. Perfectly fine. So that is one of the reason why lithium shows peculiar properties in comparison to the other elements in that particular group. Okay, very good, very good. Now tell me, why do we see a diagonal relationship between the lithium and the magnesium? Why do you think that diagonal relationship exists? There is a diagonal relationship that you find, and this particular thing is called diagonal relationship. Whenever you see a relationship between the element and its diagonally opposite element, you say that that relationship is called diagonal relationship. So if you compare lithium position and magnesium, they are diagonal to each other. So that's why it's called diagonal relationship. You will find these diagonal relationship also in other elements like beryllium and aluminum, as well as boron and silicon. There also you will find these diagonal relationship. Now, why this diagonal? What is the cause of this diagonal relationship? Is what I would like you to answer me. Think over it. You already, I think, know the answer because you have done this somewhere. I think in your second semester, probably you have done this. So let's try to answer. On descending the group, size increase, descending the group's size increase, and from left to right of the period size decrease. So on combining both effects, size remains almost the same. That is one very good reason that you have said. So if you compare the size of lithium ion, it is 0.76 Armstrong. However, the size of the magnesium ion is 0.72 Armstrong. So that means these two ions have almost the same size. Lithium ion is 7.76 Armstrong, and magnesium ion, that is Mg2 plus, has a size of 0.72 Armstrong. Similarity of the atomic radius is the reason why you see the similarity in properties. Now, as I told you, there are other elements also exhibiting this property of diagonal relationship. For example, beryllium and aluminum. Beryllium and aluminum also shows diagonal relationship, which we will be discussing as we move forward. Now, here, if I tell you the atomic radius of the ionic radius, basically the ionic radius, that is beryllium 2 plus ion radius നമ്മൾ നോക്കുമ്പോൾ, that is 0.45 Armstrong. Okay. അലൂമിനിയത്തിന്റെ റേഡിയസ് നിങ്ങൾ നോക്കുമ്പോൾ ഇറ്റ് ഈസ് 0.535 ആംസ്ട്രോങ്. ഇറ്റ് ഈസ് 0.535 ആംസ്ട്രോങ്. Okay, here what do you see? There is a difference in size. Okay, beryllium has a size of beryllium 2 plus has a size of 0.45 angstrom. However, Al3 plus has a size of 0.535 angstrom. Now, this answer you cannot give now. Now, here what is the reason why the similarities are rising? Because here you cannot just talk in terms of similarity in size, because size is comparatively different. Because 4.5 ആണ് ഒരു കേസിൽ 5.3 ആണ് 0.53 ആംസ്ട്രോങ്. So there is considerable difference in size. So you cannot talk in terms of similarity in size. There is some other reason why they are showing the diagonal relationship. Yeah, charge per unit area. Okay, charge per unit area. Charge plus radius ratio, which you can convert it to area. So charge per unit area similarity കാരണം കൊണ്ടാണ് ഇവിടെ നമ്മൾക്ക് എന്താ പറയുന്നത് similarity in property പറയുന്നത്. Because ഇവിടെ തന്നേക്കുന്നത് charge per unit area ആണ്. So charge per unit area, if you calculate for beryllium, it is 2.36. For aluminum, it is 2.5. So not much marginal changes. So charge per radius ratio അല്ലെങ്കിൽ charge per unit area. Okay, that similarity is the reason why you see the similarity in boron and aluminum. So the reason why diagonal relationship exists, you can talk in terms of size also. Another reason is because of the similarity in charge per unit area, okay, or charge per radius ratio, whatever you discuss. So that two factors are very, very important. Another similarity, if you write down the if you every element in the നിങ്ങൾ electronegativity value എഴുതുമ്പോൾ പോളിംഗ് സ്കെയിലിൽ നിങ്ങൾ electronegativity value എഴുതുമ്പോൾ നിങ്ങൾ നോക്കും ഈ diagonally related ആയിരിക്കുന്ന elementsന്റെ electronegativity value would be the same. So I think Hannah has already given that. Electronegativity similarity also is responsible for the similarity for the diagonal relationship that you observe in these particular elements. Okay, so these are the things that are regarding the diagonal relationship as well as the anomalous properties that is exhibited by lithium. So please try to read this portion in a little bit more details, and uh, we can discuss if you have any doubts when you find it. Otherwise, in the next class, probably we'll discuss the balancing of equation as well as the solubility thing that we talked about, and also we'll start with the group 2 elements. Okay, the reactivity in the group 2 elements. Anything you would like to ask me before we wind up the session? So this particular page is, if you remember, this is the 5th edition that I have. It depends upon which edition you are having. So I'll tell you the chapter. Chapter is group 1, the alkali metals. Okay, so group 1 alkali metal എന്ന് പറഞ്ഞ chapter ആണ്. So അതിൻ്റെ അകത്ത് towards the end you will find differences between lithium and other group elements. So in my book, this page number is 309. Okay, 309. Okay, anything else you would like to ask me? Otherwise, I'll just close it. So you can please go through whatever I have discussed